Following devastating droughts across most of Australia in the 1890s, an Irish-born pastoralist and philanthropist, Sir Samuel McCaughey, sought to demonstrate the benefits of irrigation at his North Yanco station. He and his team of around 200 men constructed a complex irrigation system, including more than 320 kilometres of channels, and used 2 steam engines to pump water from the Murrumbidgee River to his property. He lobbied the government to introduce an irrigation scheme, and in 1906 the Burrinjuck and Murrumbidgee Canals Construction Act passed through Parliament. The next year work began on Burrinjuck Dam, known today as Burrinjuck. After Federation in 1901, nation-building projects were gaining momentum, and Burrinjuck was the first major dam constructed for irrigation in New South Wales. It remains one of Australia's most significant engineering feats. Burrinjuck Dam provides water for the Murrumbidgee irrigation scheme, which supports one of the largest food-producing regions in Australia. It's situated high in the mountains of the Great Dividing Range near Yass in New South Wales on the Murrumbidgee River. The dam wall sits between the Burrinjuck and Black Andrew Mountains. While Burrinjuck was the original name for the reservoir, it was found to have been adopted from the native locality named Burrinjuck, which comes from the Aboriginal words Burrinjuck, meaning precipitous mountain. In February 1911, the Minister for Public Works, the Honourable Arthur Griffith, announced in the Sydney Mail that the original native name Burrinjuck would be far more suitable than Burrinjuck. The dam is fed by 4 main tributaries, the Murrumbidgee, Yass, Goodra-Digby and Molonglo rivers. Water runs into the dam from a catchment area of 13,000 square kilometres.
Burrinjuck Dam is an ideal place for a reservoir for the simple fact that we've got all that catchment area and 4 main tributaries coming in to the Murrumbidgee River, which we're looking at right here. Black Andrew Mountain, Burrinjuck Mountain, and a very narrow gorge of natural pink granite. An absolute beautifully ideal place to build a dam site.
Burrinjuck Dam is capable of holding more than 1 million megalitres of water, or twice as much as Sydney Harbour. It has a surface area of 5,500 hectares, the equivalent of 8,000 football fields, and can be filled to a height of 61 metres. Its width is 233 metres along the top. Work began on building the railway line to access the dam site in 1907. Construction of the dam wall started in 1909 and was officially launched by the then New South Wales Minister for Works, Charles Alfred Lee, after whom the town of Leeton was named. Due to labour and material shortages during World War I, the dam wasn't completed for almost 20 years. The Burrinjuck Township sprang up nearby, providing schools, churches, shops and housing for workers and their families. Many migrants from Europe worked on the dam, and it's estimated that over 1,000 people lived there during the peak of the construction phase. The wall is made of concrete gravity construction, containing massive granite boulders known as plums. It relies on the design and weight of itself to hold the water back. Its curved shape also helps to maximise the strength of the structure. When floods came during construction in 1925, water rose over the top of the dam, but, to the engineers' and workers' pride, the wall remained intact. The dam was finally finished in 1928, and since then, 2 construction upgrades to further strengthen and enlarge the structure have been undertaken. The first took place between 1938 and 1957 and was delayed by the Second World War. It raised the height of the wall to 80 metres. The final phase was completed in 1994 and added another 13 metres to bring the wall to its present height of 93 metres. This was to increase the safety of the dam during a flood and did not increase the height of the water storage. To add equivalent mass to the wall to assist in preventing the dam toppling over during the maximum predicted flood, steel wire cables were also concreted into the bottom of the structure and tensioned to the top of the wall, tying the dam to the bedrock and compressing it by 3 millimetres.
Now each cable was tensioned down to 1100 ton, which effectively compressed the dam by 3 millimetres. I believe it was the equivalent of sitting the Queen Mary on top of the dam wall to actually compress it that far. So the dam is completely safe, it's extremely strong, and it can withstand the probable maximum flood of a 1 in 100,000 year event.
Rainfall is relied upon to fill the dam, as only about 1% of the melting snow flows into Burrinjuck. Over the years, the level of water in the dam has reflected the extremes in climate conditions. Flood saw it reach 127% of capacity on the 29th of August 1974. The water level rose nearly 3 metres above the spillways and released around 400,000 megalitres a day. Substantial flooding was experienced at Wagga Wagga and many other towns along the Murrumbidgee River. The dam has also seen severe drought conditions where the level dropped to just 1.6% during March 1984. Maintaining inflows and discharges is vital to reducing water loss and preventing flooding further down the river. It's a balancing act, with daily monitoring of water levels carried out to keep the system in check. Readings are taken of upstream and downstream tributaries and river heights, providing an idea of what to expect during the next 24-hour period. A close eye is also kept on the weather, with a meteorological station on site. Every outlet on the dam can be operated by local remote control or via a radio link. There's an emergency diesel generator if the power fails, and a second manual emergency system provides further backup. Power is also available from the hydro power stations located at the toe of the dam. Nothing interferes with meeting the irrigation needs of the Murrumbidgee Valley. Even the upgrades of the dam had to be worked around supplying irrigation water. The dam structure is continually monitored by daily visual inspections and surveillance instrumentation systems, and survey points are measured annually to ensure it hasn't moved significantly. There are also inspection points inside the dam wall, where seepage is measured, along with the amount of water trying to lift the dam from its foundations. The wall itself has a degree of elasticity to protect it from cracking in the event of an earth tremor, and it has an annual movement of about 16 millimetres.
In the middle of summer, the downstream face of the wall gets extremely hot and the dam actually moves upstream. In winter, you get the opposite effect. The concrete contracts and the dam moves back from the axis.